Okay, so the principle is that you have a fluid that has to be heated, a fluid that has to be cooled down, and you can see that you can recover the heat which is available here in order to preheat the fluid which is there. So you install the heat exchanger that takes the heat here and is going to be cooled down in order to increase the temperature here. If you increase the temperature here, you have less steam to be supplied, and you have an information about how much it costs to supply the steam. Okay, so now the question is, how far do we have to go with the heat exchange area that we have here? And so what we can see is that the bigger the area is here, the higher will be the temperature here, and the lower will be the energy bill. But at the same time, it means that we will have to invest for the heat exchanger in order to save the cost of the steam, which means that we will have to compare how much we win during the year for this the steam production, and compare it with how much we pay for the heat exchanger. So it means that we have to know what is the area of the heat exchanger, deduce the cost of the heat exchanger, then make the integral of what we are going to save during the year with the steam reduction. And in reality, we have also a small additional benefit here, because if we save some energy here, it means that we will be colder here, which means that we will have as well an impact on the cooling requirements here. So there will be also a benefit from the cooling water. So in order to make the calculations, in fact, what I did propose to you was to use either to formulate the problem either as being using a sequential approach or using a mathematical programming approach. Okay. The mathematical programming approach is quite simple, because you just have to write all the equations. So you are going to write the equations of the heat exchanger here, and you are going to write the equations of steam balance and of the cooling water, and then say solve. Now I'm going, before doing the mathematical programming approach, what I would like you what I would like to explain is how you can solve it with a sequential approach. And if you have to do a sequential approach, then you have to look at the equations. And I have presented here the fluid that is cooling down, the fluid that has to be heated up, and the heat exchange between the two. So you have the fluid which is cooled down, the fluid that is heating up, and we can see that there is a temperature difference here between the hot and the cold streams. It is constraining. So if I want to increase the heat exchange, I will reduce the temperature difference here, which is then the DeltaTmin minimum. Okay, so a lower value here means that the curve, which is the black one here, will go in this direction, and I will have therefore more heat recovered, and it means that with the heat to be supplied, which is what is supplied here, will be reduced. Okay? So if I'm taking this into account, and if I'm looking at how I can make the calculations, what I'm going to do is to first say, okay, let's consider that I have identified that the DeltaTmin minimum is here, which means that I'm going to calculate. Knowing the value of this DeltaTmin minimum, I'm going to calculate the temperature here, knowing the temperature here. That's what is done here. Next step is to say, okay, I have this temperature, I know this temperature, which means that I can calculate the heat load. Okay, so second step, I'm calculating the heat load of the heat exchanger. Once I have this heat load, and as I know this temperature, I can calculate this temperature. Which means that now I know this temperature, this temperature, this temperature, this temperature for the heat exchanger and the heat load. So I can calculate the heat exchange area if I have a heat transfer coefficient. Okay? Once I have done this, then I I can also calculate, because I know this heat load here. I have therefore this one. So by balance, I can calculate the remaining amount of heat that is needed in order to reach the temperature, which is the temperature here, which means that I know how much I will pay for the hot utility. And knowing the same for the hot stream, so knowing the complete heat load that is needed, I'm going to deduce the heat exchange, the heat recovery, and I will have the heat load of the cooling requirements, which means that now I can formulate my optimization problem. So I have 1 degree of freedom, which is the temperature difference. Okay, and as soon as I have this, I have to define the value of the temperature difference in such a way that the operating cost is calculated by the cost of the cold utility, which is here, and the cost of the hot utility, which is here, both depending on the heat load that I have calculated before, that I'm multiplying by the time of operation of the unit to obtain the operating cost. And then in addition to this, I will have the investment cost, which will be calculated as a function of the heat exchange area that I have calculated as a function of the DeltaTmin minimum. Okay, which means that now, if I'm, for example, in MATLAB, I can make an algorithm that is calculating as a function of the DeltaTmin minimum, that is calculating the total cost of the system. So I'm calculating hot temperature, cold temperature, and the delta T. Knowing that this value, I can then calculate what is the heat exchange in the system. Then knowing the heat exchange in the system, then I can calculate the heat load for the hot utility, the heat load for the cold utility, the temperature. I can calculate the fourth temperature, so that I can calculate the logarithmic mean of the temperature difference for the heat exchangers. Then I can calculate the heat exchange area, the operating cost, the investment cost, and the total cost. So now I have a model that is calculating for a value of the DeltaTmin minimum, the objective function. So here I have a sequential approach. Okay, I'm starting from this one, and I'm doing this one, and each equation is giving me one of the unknown value. Okay, this is a sequential approach, and I can solve this problem, which is 1 degree of freedom optimization problem. The advantage when you have 1 degree of freedom is that you can do it by hand. Okay, you vary the DeltaTmin minimum, you plot the total cost, which is shown here, and what you can see is that it's a combination of the energy cost that is increasing if the DeltaTmin minimum is increasing, while the investment is decreasing when the DeltaTmin minimum is increasing. So the higher the DeltaTmin minimum, the smaller the area, and the bigger is the energy bill. And there is a point where the sum of the two is converging towards an optimal value for the DeltaTmin minimum. Okay?
Also, the operational cost, previous slide.
Yeah.
Where is the factor price cost?
So this is a specific cost of the cold utility, the specific cost of the hot utility. Okay, so and here you have, so it's a this is Swiss franc per kilojoule. Okay, and then no, sorry, yes, it's Swiss franc per kilojoule. Okay, and this is also Swiss franc per kilojoule of cold utility, right? Okay, so by doing this, then I have shown you the way to solve the problem with a sequential approach. Okay, if now I'm using if I'm using a simultaneous approach, the only thing that is going to change, all the values which are written here will be in fact unknown. Okay, so variables in the system. I will write all these equations. So depending on the type of software, I will have to, perhaps I will have this minus this part is equal to 0. Okay, and I will just, I will not have to give it in this sequence. Okay, I can write this equation first. I can write the second one, and then the third, this one, and then this one, and this one. There is no link between all the equations. And when you say solve in the ample system, the ample system is going to make all the variables will be varied at the same time, and it will identify directly where is the minimum. Okay. So have you read the code that I give to you? If you have read it, then you have seen that both are finally the set of equations are the same, of course. Okay. In this one, you have a sequence that has to be written. In the other one, you just put all the equations, and then the system is going to reorganize the solving procedure for you. Okay. Right, so it's important because this will be the technique that you will use in order to solve the exercise of today.
Sometimes the set of equations are nonlinear, and if the mathematical method was different method methods or to solve them.
Yeah. So if you take the mathematical programming, so here it's when you apply the sequence, you have the impression that it's not nonlinear, but the reality is that, for example, this is really nonlinear. And what you can see, the proof is here. So this is the graph, so you can see that it is really nonlinear. And the mathematical programming formulation will solve the nonlinear equations.
Many of people iteration and
that's what I was saying yesterday. So if you use mathematical programming methods, you rely on the mathematical solver, which is behind. Okay, in the case of ample, the one that is proposed is minus, which is known to be robust, but it is following iterative procedures. So it means that it is using the values that you give as an initial guess to try to start to find the right place to start. Okay? And he is doing iteration. So if the problem is highly nonlinear, and here we have a very special, but this equation is very special. Because on the one hand, if the temperature difference is the same here and here, then this degenerates, so it's not so easy to handle. And in addition to this, it's by the fact that this is then going in the denominator, it makes the solving procedure more complicated. Okay, but at least for simple problems like the one, this one, it works quite well. Okay.